Okay, so we got a quiz coming up, and quiz is on second order circuits, and the test is on everything from inductors to capacitors on up. We're going to get this stuff out of our system and move on to the fun stuff, which is AC circuits, which would be starting in week 13. Thanks, Matthew. So this week we're going to do one last assignment on second order circuits. We'll be doing the step response of second order circuits. How did you like last week's homework? No? Something left behind? Okay. Sure, no problem. And so this is anyway, these RLC second order circuits, they're kind of a pain, as we saw in class and then out of class. Oh, I was going to show you a cool example of a second order circuit. A buck converter is a DC to DC power converter which steps down voltage while stepping up current, or vice versa. You can make a boost converter. And what's cool about this, so these are all really abstract, right? What do we, what's the good, what good are these things? You're doing all this stuff. But here is a circuit. Oh, that's just an inductor. But you can see, let me just see, boost converter. It's a boost converter. Now it has a diode in it, but it's actually still, analyzable using a lot of RLC stuff. So you have a inductor and a capacitor, and suppose you want to get, your voltage source maybe is only 5 volts, but you want to sort of somehow get 12 volts to your load. What could you actually do? Well, what this does is it actually powers we sort of have a switch here, which is implemented with a transistor right here. And what you do is you charge up the inductor so it has a current going through it, right? And then you open the switch, and where does that current go? Remember, the inductor current can't change instantly, so where does the current go after you open that switch? It flows right through the diode and charges up the capacitor. And inductors make a big spike when their current shuts off suddenly. They don't like that, a big voltage spike. So that voltage spike will actually exceed the voltage of your power source. And so it will actually get a higher voltage on the capacitor than you actually have on your voltage source. And then once you close the switch again, you're recharging the inductor. The capacitor is sitting there with a high voltage, and it can't go back through the diode, right? It's blocked. It can only go out through the load. So basically, if you keep pulsing it fast enough, you can provide enough charge. It's going to be oscillating somewhat, but it will get to a higher voltage than your input source. David? The diode's like a one-way street. Yeah, diodes only allow current to flow in one direction. So that's an example of a cool example of a pretty practical application of RLC circuits with a couple extra components. just so they're not just these things that we feel like we're torturing you with. So we're going to now look at the step response. The step response is where you actually have a source attached to it, and for t greater than 0. And here's the typical circuit. You have an RLC series circuit, and the switch closes at t equals 0, so we start charging. So initially, we would be given, maybe there's some initial current, some initial voltage. Again, you have to sort of find that out eventually. But if you have those initial conditions, we're going to find V of t across the capacitor. And in this case, this is still a second order circuit. It is linear. It is non-homogeneous. And it has constant coefficients. So we analyze this using voltage, which is interesting. The equation works out easier to do the analysis in terms of voltage. If you have an I flowing through the circuit and you have a VL here and a V, when t is greater than 0, you can derive the governing equation using KVL. So you can have minus Vs plus R times I plus VL plus V equals 0. And we know, because of all these relationships, that I equals C dV dt. And VL equals L di dt. Oops, wrong arrow. Let me fix that. VL equals L di dt. So to continue, you would have minus Vs plus RC dV dt plus L times d dt of C dV dt plus V. That's still just KVL. So rearranging things a bit, you're going to get LC second derivative of V plus RC first derivative of V plus V equals Vs, your source voltage. And we can consolidate that into a single standard form t squared v dt squared plus R over L dV dt plus V over LC equals Vs over LC. Okay, so that is the equation. And you can consider that there are going to be two parts, as you are probably familiar with, the homogeneous and the steady state response. The homogeneous response is where it equals 0. Sort of have seen this before, except it was in terms of I. That equation it's the same thing. You know, you get the it's e, you know, v of t equals a e to the st. You get the roots and all that stuff. Can we fast forward to this? Do I have to write all that out again? It's the same s1, s2 You know, so let's just say, you know, v of t equals some a e to the st, and s, you know, s equals minus, let's just go straight to the chase, minus alpha plus or minus the square root of alpha squared minus omega 0 squared, where alpha equals r over 2l, and omega 0 equals, omega 0 squared equals 1 over LC. So it is the same form as the series, except we're using volts instead of current this time. And case 1 is, of course, v of t equals a1 e to the s1t plus a2 e to the s2t, which is overdamped. Case 2 is v of t equals e to the minus alpha t times b1 cosine of omega dt plus b2 sine of omega dt. And that's where, you know, omega d equals the square root of omega 0 squared minus alpha squared. And case 3 is when v of t equals e to the minus alpha t times a1 plus a2t. Is this how your differential equation class is? They just keep throwing this stuff at you over and over again? Or is it, it's not as repetitive, right? This is just really repetitive. It's the same thing over and over again, doing this 4 different types of second order circuits. And in the steady state, so that's the homogeneous solution as we've seen already. This is the way we kind of set up that part. And in the steady state, that's where, you know, we worry about what's happening at infinity when dv dt equals 0. And if you look at the equation, the original equation, when all the derivatives go to 0, you just kind of cancel those out. The steady state, that goes to 0, that goes to 0, and you're left basically with the idea that v infinity has to equal vs. What that means in the series RLC circuit, right, all of the voltage drop eventually just takes place over the capacitor, because with a series circuit, when everything dies out, the inductor turns into a short, but there's no current going into the capacitor. The capacitor is an open, and the open kind of rules a series circuit. Right, so, you know, even though this becomes a short circuit in the steady state, this is an open circuit, meaning the I is going to equal 0 at infinity. So all the voltage drop takes place across the capacitor. That's all I'm saying. That makes sense. So we can think of this again, second order. What? That's weird. Got the same slide twice. So yeah, second order. So basically, actually, I think it'd be better to squeeze this in if we can. So in general, right, v of t I don't know, or there isn't really that much room here. Let me go to the other page. So so v of t equals v infinity plus v transient, right? So this is the steady state and the homogeneous, right? So this is the steady state, and this is the homogeneous. So we just add, in other words, just add those two together. So V of t equals our V infinity, our final value, plus the homogeneous solution, e to the S1t plus a2 e to the S2t, depending on your case, right? That's case one picture, right? Yeah, Mason. Transient, yeah. Transient. It's ephemeral. It doesn't last very long. So TR equals transient. So like if you're looking at this on an oscilloscope, you have to have the time base set up properly so you can even see the transient, right? Because otherwise, if your time base is too long, you're just going to see the steady state value. The transient will happen so fast. So it dies out rapidly, or it eventually dies out, leaving only the steady state. And of course, your A1 and A2 are from the initial conditions. And the no jump rule. So here we have example 4. And of course, they can always sort of mess with things so that it's it's always sort of a unique configuration. But here we have an RLC circuit, and the switch is opening up across the resistor that's connected to the capacitor. So, and of course they don't tell you this, the switch is closed a long time. And it opens at t equals 0. When you see this symbol, that's really what that means, right? That symbol of a switch where the arrow is showing you what's happening at t equals 0. It was closed and now it's opening, right? So you have to be able to see that and interpret that properly. So for t greater than 0, this is a series RLC step response. Right, it's series because when that switch is open, you just have one loop there. And so our V of t is going to equal V infinity plus V transient. And our V infinity is just going to equal our Vs, which is going to equal 12 volts. That's pretty easy. The challenging case, of course, as usual, is the transient, which is the homogeneous solution. The transient is, you got to figure out, which case is it. So for series, the values of S1 and 2 are going to equal minus alpha plus or minus the square root of alpha squared minus omega 0 squared. And alpha equals r over 2l. And L is, what is it? L is 1, so it's just 2 over 2, which is 1. And omega 0 squared is going to be 1 over LC. And the C is a fifth, so it's basically 1 over 1 times 1/5. Oops, that's a 1/5 there, sorry. So that equals 5. So our S's are going to be -1 plus or minus the square root of 1 squared minus 5. And that's going to equal -1 plus or minus J2, which gives us case 2. So our V transient, you're just looking at that transient part, is going to be e to the -1t times a1 cosine of 2t. Wait a second. That is omega d, right? Yeah. So this implies omega d equals 2. So a1 cosine of 2t plus a2 cosine of, sine of 2t. Now this is just the transient, right? So we don't apply initial conditions here. We actually have to look at the whole solution and apply the initial conditions to that equation to make sure everything works okay. So the total solution is going to be V of t equals V infinity plus V transient. Well, how do we know it's case 2? Case 2 is when, well, does it show up here? Let's see. Case 1 is when alpha squared is greater than omega 0 squared, so that your roots are both real, right? Case 2 is when alpha squared is less than omega 0 squared. And case 3 is when alpha squared equals exactly omega 0 squared. Yeah, you're just comparing those two values. Thanks, good question. So, so we have this is our transient solution, but we can't forget that V of t is going to equal our V infinity value plus the transient. So our V of t is going to equal 12 plus V to the minus t times A1. Now we're changing the orders. You want A1 to be sine or A1 to be cosine? Why am I? Okay, I guess we're going to switch it so that A1's going to be the sine. A1 sine of 2t plus A2 cosine of 2t. It doesn't matter as long as you're consistent. So, right, so we've got the equation, and we have to, at this point, all we got to do is find A1 and A2. That's really the hardest part of these, right? Matching the boundary conditions. A1 and A2 are the initial conditions from no jump. VC of 0 plus equals VC of 0 minus, and IL of 0 plus equals IL of 0 minus. So as usual, we have to draw the circuit at t equals 0 minus to figure out what those initial values are. At t equals 0 minus, we've got the R. And the first R is, what's this first value of R? The first value of R is 2 ohms. I guess both R's are 2 ohms. Interesting. Okay. So we have a 2 ohm resistor, an inductor, a capacitor, and another 2 ohm resistor. Oops. The switch is closed, so that resistor is in place there. The inductor at t equals 0 minus is like a short, and the capacitor is like an open. So this is our IL of 0 minus going through the inductor. And this is our VC of 0 minus across the capacitor. Okay, quiz time here. Steady state, inductors is short. Capacitors an open. What is IL of 0 minus? This one's actually not too hard. 3 amps, right? Because if that inductor is a short, you got 12 volts. The 2 ohms here and the 2 ohms there are taking that current from 12 volts to ground, right? So it's 12 volts over 4 ohms. So we have 3 amps. And what is VC of 0 minus? Alex? No. Remember that switch is closed, so current's going through that 2 ohm resistor alongside the capacitor. It will be 12 in infinity, but at 0 minus, when that second resistor is switched in there, Daniel, what's the voltage across capacitor? 6 volts, right? Because you got a voltage divider, right? You're going to be dividing that 12 volts across 2 resistors of the same value. So that's 6 volts, which is VC of 0 plus. And this, of course, is IL of 0 plus. It's 3 amps. So what this is telling us is that VC, which is the V that we're trying to solve for here, because it's the V that's labeled on the circuit, we're trying to find V there. We know now what that has to be at t equals 0. It has to be 6. So that's one boundary condition. V of 0 has to be 6 volts. But what about dV dt at t equals 0? And these are actually 0 pluses. dV dt at t equals 0 plus, what is that? Well, what do? We have to draw that circuit now at t equals 0 plus. You kind of did this already, right? So this should be somewhat familiar. T equals 0 plus, you've got your 12-volt source. You've got your 2 ohm resistor, your inductor, and your capacitor. Now the two things that don't change are death and taxes. No, are IL and VC at t equals 0 plus. So IL of 0 plus is going to equal 3 amps. And VC of 0 plus is going to equal 6 volts. And from this, we will deduce what the slope is of the voltage, because dV dt equals what? Why do we have the 2 ohm resistor on it? Because, thank you for asking, the 2 ohm resistor has been disconnected from the switch by the switch. So if you want to draw in a phantom 2 ohm resistor, it's no longer connected. Maybe that's too confusing. We could also just draw those terminals there indicating that there was something there, but no longer. So that is gone. So we have to now infer this, right? So we got to figure out what is dV dt, and we're going to use what to figure out what the slope is? Mark. Yeah, IC divided by C. IC of 0 plus is divided by C is going to just give you the current through the capacitor divided by C. That'll give you the rate of change of the voltage, and that is going to be pretty easy. That's just 3 over 1/5, because IC is the same as IL in this case, right? But IL is going plunging straight into the capacitor, so that equals 15 volts per second. So that's our second boundary condition. Okay, so now we have two equations, and so we can solve. Our V of 0, according to our equation, is going to equal 12 plus e to the minus 0, right, times A2 cosine of 0t plus A2 sine, I'm sorry, omega d times 0. Or actually, let's just say 2 times 0 plus A2 sine of 2 times 0, right? And that goes to 0, right? So we're just left, and this goes to 1. So that just equals 12 plus A2. This goes to 1. (12 plus A2). Therefore, oh, and it must equal 6. So therefore, A2 has to equal minus 6. That is our first condition. Oh, because I am. Let's see. What did we decide was the coefficient of the cosine? The cosine was A2. The sine is A1. We have to stick with that. Thank you. Okay. The other thing we need is we got to figure out. Okay, so it's kind of messy. dv dt equals. So dv dt, when v is this equation right here, we have to differentiate this thing, right? It's a sum of two sinusoids. And because there's an exponential multiplying it, right, we have to do the exponential times the derivative of the sinusoids plus the sinusoids times the derivative of the exponential. So it becomes kind of long and messy. So it's going to be minus e to the minus t. So that's the derivative of the exponential times the two sinusoids, a1 sine 2t plus, I should say, now we know a2 is minus 6, so it's going to be minus 6 cosine of 2t plus e to the minus t, the exponential, times the derivative of the sinusoids, which is going to be 2a1 cosine of 2t plus 12 sine of 2t. That's the derivative of minus 6 cosine of 2t. So therefore, dv dt at t equals 0 is going to equal, kind of crossing out all the terms that don't matter. It's going to equal, so the a1 is going to be 6. So this goes to 0, right? That goes to 1. It's going to be 6 plus, and then that goes to 1. It's going to be 6 plus 2a1. And that has to equal 15 from what we've learned before. So therefore, a1 equals 4.5. That is our second coefficient. So then we can put it all together and say that v of t is going to equal 12 plus e to the minus t times 4.5 sine 2t minus 6 cosine of 2t. Yep. Where did the 15 come from? That was this 15 right here. So this is our second boundary condition. This was our first boundary condition. And we're basically matching things up so that A1 and A2 make those things true in our solution, right? We have to choose A1 and A2 based on those two things. First boundary condition, second boundary condition. That gives us these two values, A1 and A2. I don't know if I should call them 1 and 2. I'm just going to call them A1 and A2 like that. And that's our solution. Now we're also asked to find I of t. So I of t, of course, is c dv dt. Oops, too many question marks. I of t equals And I of t is going to equal C dV dt in this case. Yeah, anyway, because of the way the circuit is set up, the capacitor is kind of ruling this circuit, right? And so you can take the derivative and do it that way if you want. So we basically take the derivative of that. Or you can solve for I of t directly. And I need a new slide here. You can find I of t directly because I of t is going to have the same form as V of t. It's going to be some I infinity plus some I transient. The thing about I infinity is, what's I infinity going to be? Yeah, it's going to be 0 because we already figured that out. There's no current flowing in the steady state. So I of t is going to be simpler. It's just going to be e to the minus t times some different constant b1 cosine of 2t plus b2 sine of 2t. The initial conditions are that IL of 0 is going to equal 3 amps. VC of 0 is going to equal 6 volts. You'll have to figure out what di dt is. T equals 0 plus. But that's going to just be a VL of 0 over L. So you can do KVL at 0 plus, and in that original circuit, and you're going to have minus 12 plus 2 times 3, this is the R times I, right? Plus VL of 0 plus 6, which was the initial capacitor voltage, has to all equal 0. And when you add all that up, that tells you that VL of 0 plus equals 0, so that your I of 0 equals 3 amps, and your di dt at t equals 0 equals 0. So you can just plug those into the general form and solve, right? So it kind of, since there isn't really a steady state value for current, it's sort of like a homogeneous response, really, typically. Simply it kind of devolves into a homogeneous response because there's no final value for current. Final value for current is 0. So we could plot these in Wolfram alpha again. I think it's always sort of interesting. I'm going to try to include those plots in my future. So we could plot, 12 plus x of minus t times 4.5 sine of 2t minus 6 times cosine of 2t. From, and we want to go like about 5 time constants or so. The time constant here is 1 second, right? So if we go out t from 0 to 5, that should give us both the picture of the transient and the final value. And this is sort of the classical underdamped solution, right? It's a decaying exponential. It's rising up past the final value. It goes way up to 15 volts or so. And that's why you can see if this was in one of those boost converters, you're getting 15 volts temporarily. You could be sucking that current out and charging a capacitor on the other side of a diode there. And then it drops down and steadies out at 12 volts. So that's the solution for the voltage. If you wanted to, you could try to differentiate that. And I don't know if this is something you could just tell Wolfram Alpha you wanted to do. Like, could we just say plot the derivative of? Probably not. But it is getting better at recognizing, oops, I have to go to Wolfram first. It is getting better at recognizing English descriptions, which is kind of cool. We'd also have to divide it by C, so this is just going to be, yeah, that's sort of the right form, right? We'd have to divide that whole thing by, what was the capacitance? 1/5, right? So we have to actually multiply that times 5. So we, sorry? Oh yeah, it's C. It's C times C, so it's divided by 5. Okay, so it is, so plot 0.2 times the derivative of, so it should change the scale on that, but the shape should be the same. And what did it do? It screwed it up. Interpreting as, yeah, it doesn't like that. So the derivative, we would actually probably have to sort of divide this whole thing by 5. 12/5 plus 1/5 times, how's that? You can have so much fun. Anyway, that is, that's pretty much it right there. So that is the current. It's missing the initial value. It's annoying. It should take it all the way to 0. I'd like to see that 0 value, but anyway, you get the idea. That's the general shape. It starts off at some initial value. Well, it should start off at what? It should start off at 3, right? Starts off at 3 and then kind of works its way down. Crosses over, becomes negative for a little bit. So, and then what's happening again is the energy is kind of shifting from the initially, right? The energy is sort of distributed between both the inductor current and the capacitor voltage. There's some in both, and they're kind of, after the switch throws, they're kind of circulating the energy back and forth a little bit until finally the capacitor ends up with all the energy. Right? The inductor has actually dumped all the energy because there's no current flowing, but the capacitor has charged up and it's storing all the energy at the end. You can see like this. So I think of it a lot of different ways, like a slinky or something, where stuff is moving back and forth for a while until it freezes. So we have one more of these tomorrow. Well, step response with a parallel RLC, we'll do that tomorrow, and then a general second order circuit. So there's sort of 2 more cases before we can be rid of this awful experience. Sure. Yeah, they're very painful. All right, catch you guys later. Yep.